Hello everyone. Today I will be presenting on a framework for integrating digitized design charts into AI-driven geotechnical applications. While the examples I will use focus on foundation design, the same principles can be applied to a wide range of other engineering solutions. Before we begin, let me introduce some of the key terminology that will be used throughout this presentation. API, or Application Programming Interface, refers to a set of rules that enables different software applications to communicate and interact with each other. LLM, or Large Language Model, is an AI model trained on large volumes of text data to generate human-like language. RAG, or Retrieval Augmented Generation, is an AI approach that combines document retrieval with text generation to produce accurate, domain-specific responses. Here's an overview of my presentation. I will start by introducing Level 1 applications, simple but practical tools I've been using over the past few months. From there, we will move into Level 2 applications, where I will show how generative AI can support engineering calculations. I will also demonstrate how traditional design charts can be integrated into a customized GPT to streamline workflows. Finally, we will look ahead to Level 3 applications, exploring how AI might continue to evolve and reshape the engineering industry in the near future. Let's start with one of my favorite AI applications. This in-house tool uses an AI agent to automatically process core photos. It captures the key information, renames the files, generates a CSV summary, and prepares complete photo records, all in just a few clicks. The workflow is simple. Just select the job folder and choose a record template, and the system takes care of the rest. Behind the scenes, this application combines optical character recognition (OCR) and large language models (LLMs) to streamline what used to be a very manual process. Another simple but very practical application is summarizing laboratory test results. Imagine you have received a stack of particle size distribution reports, and the lab hasn't provided a summary sheet. For some reason, that happens often, and it means you are required to enter the percentage of passing values manually into a summary table. With an AI agent powered by OCR and LLM, this process becomes straightforward. The system extracts the required data, maps it correctly, and produces a complete Excel summary file in just a few seconds. This slide shows the prompt provided to ChatGPT. It includes instructions to guide the LLM on what information we need and the desired output format. We can take this idea a step forward by using an online platform called N8N. This workflow software allows us to automate the entire lab test summarization process. Unlike the earlier example, which relied on a single LLM, this approach combines multiple LLMs with Python scripts to create a more complete engineering workflow. Here's how it works. When a new file is uploaded to a designated Google Drive folder, the system automatically detects it, triggers the workflow, and generates a summary table in Google Sheets with no manual effort required. So far, the examples we have looked at focus on routine tasks in fieldwork and laboratory testing. They're efficient, practical, and save a lot of time. but they don't really require deep engineering expertise. That naturally raises a key question. How capable is AI when it comes to actual engineering design and analysis? To explore this, we will now move into more technical applications. In the next examples, I will demonstrate how machine learning, OCR, and LLMs can be applied to real engineering challenges. Today, I will be focusing on Category 2 methods for foundation design and analysis. These methods are mainly based on fundamental mechanics principles and often incorporate the use of empirical design charts. While these methods are well established and widely used in practice, we can still explore opportunities for automating these methods using AI. I won't go into too much technical detail. Instead, I will focus on sharing the concepts. The same principles can also be extended to other engineering solutions, such as retaining wall design, slope stability analysis, and tunnel design. Let's start with the first example, calculating the settlement of a shallow footing. In the governing equation, there are three inference factors, IF, IE, and IG. IF and IE can be obtained directly using closed form equations. IG, however, is chart dependent. Traditionally, completing the settlement analysis requires engineers to interpolate the IG value from a design chart, a process that can be time-consuming and prone to inconsistency. Now, the process becomes much simpler. You can take a photo of your hand sketch and upload it to a customized GPT model. Using computer vision and OCR, the AI agent interprets the sketch, extracts the key parameters, and provides the values of IF, IE, and IG. It then completes the calculation and provides the settlement result automatically, saving time and eliminating manual chart lookups. Example 2 focuses on calculating the settlement of a pile. This method is entirely chart-based, which means that to complete the calculation, engineers must extract 4 different parameters from design charts. Once again, the process is straightforward. Simply take a photo of your hand sketch and upload it to the customized GPT. Within seconds, the AI agent extracts all the required parameters directly from the design charts and calculates the pile settlement for you. This not only reduces manual effort, but also significantly speeds up the entire analysis process. So, how can we build this kind of customized GPT? The key lies in digitizing our engineering knowledge and making it machine readable. That means converting traditional design charts into digital form. Here, machine learning approaches play an important role. Due to time constraints, I will just walk through the basic concepts. Here's one approach to digitize design charts. In example 2, we need 4 correction factors, I1, RK, RB, and RV. For this demonstration, let's focus on the most challenging one, RB. This is essentially a 4-dimensional problem where the values of RB depends on 3 independent variables. Finding a closed-form solution for RB is extremely difficult. Instead, we can take a different path by training a artificial neural network to model the relationship. To train the artificial neural network model, I use data extracted from the 5 charts shown earlier with an online tool called RepPlot Digitizer. This slide illustrates the neural network architecture which consists of 5 hidden layers. After training, I evaluated the model's performance using mean squared error, mean absolute error, and the auto score. The auto score is close to 1, indicating that the model provides an excellent approximation for the input data. Once the training is complete, we end up with a digital machine learning model that effectively serves as the equivalent of the original design charts. This transforms the manual chart-based process into a fast, automated, and scalable solution. Here is a test using an unseen data point. By inputting the independent variables shown on the screen, we can automatically obtain the RB value using just a few lines of Python code. The result is 0.659, which is nearly identical to the value obtained through direct measurements on the chart. This slide shows the original design chart and a graphical representation of the equivalent digital ML model. Although the 3D plots of the ML model display only 8 values or layers, the L over D ratio is treated as a continuous variable within the model framework. The next step is to integrate the digital machine learning model into ChatGPT. We can do this using a technique called Retrieval Augmented Generation, RAG. Don't worry about the technical jargon. For our purposes, you can think of it as simple adding a domain-specific knowledge base to ChatGPT. This way, the model can provide engineering insight based on digitized engineering knowledge. To build the knowledge base, we need to upload our engineering resources. These can be as simple as basic instructions, design rules, or prompts, often stored in something like a Word document. In this case, I've also uploaded 2 large CSV files containing the data for the correction factors. Together, these resources form the foundation that allows the customized GPT to deliver accurate engineering-specific results. Here's how the customized GPT works in practice. The AI agent uses the uploaded dataset to search for the nearest matching values, and then performs the request calculation according to the prompts. The customized GPT follows these instructions step by step to deliver the result. One important note, the CSV files are only needed when using ChatGPT's interface. For other platforms, like Ollama or direct OpenAI API calls, you can simply extract the requested correction factors directly from the machine learning model using Python code. Of course, validation is essential. To test the accuracy of the machine learning approach, I use Placis 3D to simulate 4 different scenarios. The comparisons shows very good agreement between the machine learning predictions and the numerical simulation result, giving confidence that the approach is both reliable and practical. Similarly, this approach can be used to create your own domain-specific GPT. By digitizing your expertise knowledge and embedding it into the model, you can develop a customized AI tool tailored to your engineering needs. Whether it is for retaining wall design, slope stability analysis, tunnel lining assessment, or other applications. Looking ahead, can we automate the entire foundation design process? This is the framework I am currently developing. It simulates the full workflow of foundation design, which typically involves site investigation, data interpretation, ground model development, calculation, and reporting. In this framework, each task is carried out by a dedicated AI agent. These agents are interconnected, working together to cover the entire design workflow. As we have seen, we already have examples like the lab test summarization agent and the prior settlement analysis agent. Over time, more specialized agents will join this family to complete the ecosystem. Here is another important member of the framework, the task routing agent. You can think of this agent as a general practitioner in medicine. Just like a GP, it understands your design brief, organizes the relevant data, prepares a referral note, directs the task to the most suitable specialist agent. This ensures that each part of the design process is handled by the right expertise within the AI ecosystem. I'll be sharing more details about the automatic design framework at the Piling and Grant Improvement Conference 2026. These are the key reference papers for this presentation. Last but not least, I would like to express sincere gratitude to Professor Harry Polos and my supervisor, Craig Johnson, for their valuable review of this paper. Here is the final thought I would like to share. When it comes to AI application, people often ask a question, what can AI do for me? I believe a more proactive and powerful question is, what would you like AI to do for you? That mindset opens the door to innovation, creativity, and solutions tailored to our real challenges. Thank you for watching.